Okay. So, in the just we have seen that delta is equal to 0.39 to P upon 273 plus T, this is equation 43. Now, we will come to the your corona power loss, right. So, whatever your visual critical voltage, disruptive critical voltage, all we have seen. Now, we will come to the corona power loss, right. So, basically the power dissipated in the transmission line due to your corona discharges is called corona loss, right. So, estimation of accurate corona loss is very difficult, right. It is almost impossible, right, because of its extremely variable in nature, right. It depends on so many factors associated with it. So, all these things have been explained. So, what happened? So, basically if you see in under fair weather condition, right. So, corona will be very small, but under foul weather condition corona will be very high, as high as 10 times than the corona loss of the your fair weather condition. So, that is why there is no you cannot give any formula for exact formula for corona loss, but some empirical formula is available. I mean through the experimental test people have found some approximate formula. For example, F.W. Peak actually he gave this corona loss under fair weather condition, and is given this formula is it is under fair weather condition, right. It is something like 244 upon delta into A plus 25 into V n minus V 0 whole square into root over R by D into 10 to the power minus 5 kilowatt per kilometer per phase, right. So, that means this corona loss it is under fair weather conditions, that means corona loss if you look into that it is inversely proportional to the delta, that is air density factor, directly proportional to the frequency, directly proportional to this V n minus V 0 square, and also directly proportional to your root over R by D, right. So, in this example for this formula P is the corona loss, PC actually is the corona, here I have written PC. So, here it is PC, PC is the corona loss, F is your supply frequency, delta is your air density factor, and V n is RMS phase voltage, line to neutral voltage in kV, and V 0 is RMS value of disruptive critical voltage per phase in kV, this is V 0, R is the radius of the your conductor, and D is the spacing or equivalent spacing between conductors. If it is a single phase then it will be D, if it is 3 phase then you have to find out DEQ, that is your you know that DAB, DBC, DCA to the power 1/3, right, into 10 to the power minus 5 kilowatt per kilometer per phase. So, this is actually your what you call that corona loss formula under fair weather condition. So, therefore, it is to be noted that for a single phase line V n should be half into line voltage, and for a 3 phase line this we have given earlier also, it is 1 upon root 3 into line voltage. Now, Peak's formula for corona loss is valid when corona losses are predominant and the ratio V n by V 0 greater than 1.8. If this ratio is greater than 1.8 then Peak's formula of corona loss is quite valid, right. But when V n less than V n by V 0 less than 1.8 this ratio, the following formula known as Peterson's formula gives better result. So, there is another formula for corona loss, that is called Peterson's formula if V n by V 0 your less than 1.8. So, in this case that corona loss P c is equal to 2.1 into F in bracket V n upon log base 10 D upon R bracket close, this is whole square into 10 to the power minus 5 into capital F, this is capital F kilowatt per phase per kilometer. What is capital F? I will be coming. So, P c is the corona loss, F is your supply frequency, your V n is the your RMS voltage line to neutral in kV, R is equal to radius of the conductor, and D spacing or equivalent spacing between conductors, and F, this F is the factor actually F is called the corona loss function, right. I mean you have for different ratio V n by V 0 you can find out what is F. It varies with the ratio V n by V 0 and is given below in tabular form, I will show you. So, F actually is a variable, right, it depends on the V n by V 0 ratio, that although in this function V 0 is not coming in this equation, V 0 is not coming, but F is a function of V n by V 0, that means this P c actually is a function of V 0 also. right. So, in this case that your Vn by V0 this side and this is your F. So, when it is 0.6 it is 0.012, 0.8 0.018, when it is 1 it is 0.018, when it is 1.2 it is 0.08, when 1.4 it is 0.3 increasing I mean in a very rapid manner when Vn by V0 is increasing, then 1.6 it is 1, when it is 1.8 it is 3.5, and when it is 2 it is 6, almost 3 times, and it is 2.2 it is 8.0. That means, when Vn by V0 ratio is increasing, this F is also increasing in a very faster rate, right. So, this I mean if you solve the numericals and if Peterson's formula is given, then this table will be supplied such that you can have the data from this table. Next one is that is your factors affecting the corona. So, first one is the effect of system voltage in a transmission line, right. For example, you take any two phase conductor, right, and if you see the voltage applied across them is more, then naturally that potential your this thing electric field intensity also will be more, right. That means, any two conductor you take, if potential difference is high, then electric field intensity is also very high, right. Therefore, and hence the corona loss also will be very high, as seen from equation 44 and 45, right. When Vn is large as compared to, I mean 44, 45 just I showed you. This is 45, this Peterson's formula is 45 and your Wick's formula is 44, this one is 44, that is your FW Wick's formula for corona loss, right. So, when Vn is large as compared to V0, corona loss increases, right, at a very faster rate with increase in voltage, because those are directly related to your Vn and your V0 both, right. So, this is the effect of system voltage. Next is effect of frequency. Now, again in equation 44 and 45 we have seen the corona loss actually is directly proportional to the frequency, right. That means, this here also F plus 25, that is F plus 25 is a constant. So, it is directly proportional to this, and similarly your this Peterson's formula here also directly proportional to F. So, that is it I mean it depends on the frequency, right. So, as seen from that it has directly proportional to the frequency, but in a power network 50 hertz or 60 hertz there is not much change from the nominal value. If nominal is 50 hertz, there may be slight increase or slight decrease depending on the power system condition, right. Next is effect of density of air, again from equation 44, right. It is evident that because we have seen the air density factor that corona loss is inversely proportional to delta. Therefore, equation 44, that is your Peck's formula, just now I showed you many times. It is evident that corona loss is inversely proportional to the air density factor, that is delta. That is, corona loss increases with decrease in air density factor, your air density decrease, your what you call decrease of density of air, right. So, corona loss of a high voltage transmission line passing through as a hilly area, right, may be higher than that of similar transmission line in plains due to the lower value of delta at high altitude. But because when you are at higher altitude, particularly hill area, right, your what you call that your I mean dust or dirt, whatever it is hilly area in altitude it will be less as compared to the plain areas, right. So, that is why that similar transmission line in place due to the lower value of delta at high altitudes. If delta is your low, then your what you call that corona loss is proportional to inversely proportional to delta. So, that is the corona loss of a high voltage passing through a hilly area may be higher, because your delta your this thing then that of similar transmission line in plains due to the lower value of delta at high altitude, right. So, if that is the thing. So, next is your I mean it is inversely proportional, right. If delta is high, corona loss will be low. If delta is nearly 1, right, then corona loss will be your what you call low. Next is effect of conductor radius. Now, you know that conductor radius, that potential gradient at the surface of the conductor is high if radius is your what you call small, right. So, particularly but anyway at the surface of the conductor it is higher, right. we know that q upon 2 pi epsilon 0 into r. So, that means if radius is high, the surface field intensity is less, hence corona loss is less, right. For the same current carrying capacity, say on ACSR, your conductor has larger radius than single copper conductor, right. Therefore, transmission line of ACSR conductor have lower corona loss than copper conductor lines. For bundle conductor lines, effective radius is high, hence corona loss is less, because if effective radius is high, then potential gradient that will be also less. So, hence the corona loss is less. It is from your intuition you can come to this conclusion. Now, another thing is that effect of rise of your temperature rise of conductor by load current. When load is high, so conductor will carry more current, therefore, there will be a temperature rise in the conductor, right. That means, the conductor current raises the conductor temperature, hence leading to an indirect reduction in corona loss, although right. That is your, although delta is related to your pressure as well as both temperature, right, for computing that your visual critical voltage, right. So, corona loss is larger if the conductor temperature is low, right, and this is due to the fact that at the low temperature, the dewdrops collect on the conductor surface during fog and humid weather. High conductor current prevents such condensation and reduces corona loss. So, indirect effect is there for the your what you call the loading of the power system, because if load is more, then your conductor will carry more current. Then another thing is that effects of snow or frost layer, particularly in that mountain side, that effect of snow or will be there, it is very much there, particularly in the hilly areas. So, snow or frost layer on transmission line conductor causes very high corona losses and of course, the radio interference, right. This layer is found if temperature is 0 degree centigrade and remain for longer duration if temperature are lower. I mean, if it is 0 degree or below 0 degree, that is minus temperature, hilly area which is very common, right. So, this phenomena you will see that snow or your frost layer will be there on the conductor, overhead conductor, right. So, corona discharges with conductor surface covered with snow and electric field intensity not exceeding 30 kilovolt per centimeter, consists mainly of pulses in negative half cycles and pulseless steady corona at positive half cycles, right. So, corona discharges themselves which affect the form of snow layers and often blow up the snow in the neighboring regions of corona. That means, suppose your what you call it is a high voltage line and that is conductor is covered by snow, and if your what you call that corona happens, then what will happen that due to this corona discharge that snow will melt in any way. At the same time, on the conductor nearby areas nearby region of the conductor, that snow will be blown up, right. So, this is very common phenomena, and if you go to any hilly area, particularly an overhead transmission line in winter, you can see that conductor is covered in by snow. This is very common phenomena, and particularly this happens for your what you call for overhead conductor. Next one is corona loss of new and old conductors. If the conductor is a new one, I mean, suppose you are putting a new transmission line, right. So, corona loss is more due to scratches, burns, etc. for the new conductor, but over the time as the line ages, corona loss decreases. The old conductor is called weathered conductor, because it is season conductor. Suppose it is there for a few years, so it is called weathered conductor. So, once one engineer asked me something like this: suppose you are 3-phase line, this is a question to you, 3-phase line, suppose out of these 3 phases, say you are putting in 2 phases, suppose you are replacing 2 phases the old conductor, say 10-12 years old conductor, a new conductor, and third one is an old one. So, and it is a balanced system, it is carrying equal power, I mean balanced system, right. Supposed to carry equal current as well as your voltage also balanced, no question of unbalanced thing. You take ideal case balance, then which conductors will carry more power, the new conductor, both new conductors or old conductor? You assume it is a balance. This is a question to you. When you listen to this lecture, you try to answer this question, you send me mail, and if you can correct answer, I will appreciate that. I reply within 2-3 days. I reply whatever mails in the previous course I have received. I think I have answered to all of you. I did not leave anyone. I gave all answers. Right. Next, effect of supply voltage. If the supply voltage is high, right, coronal loss will be high. This is very common, right. If supply voltage is high, coronal loss will be high, right. If in low voltage transmission line, coronal loss is negligible due to insufficient electric field to maintain self sustained ionization, because at low voltage, that is electric field intensity cannot be maintained, right. That is why coronal loss, it happens mostly 220 kV or above voltage level. Particularly, in rainy season, if you, I mean, you try to experience this. In rainy season, if you see that overhead conductor, say 220 kV line, you will find some kind of chattering noise, even in the daytime also. That is mostly happening due to coronal loss, right. Although daytime, that violet glow or visual glow may not be visible because daytime, but night time it is possible, right, and particularly in the dark areas, those will be very prominent, and this violet glow due to the ozone gas, right. Then effect of dust and dirt. In the presence of dust and dirt, it required voltage gradient is less for maintaining sustained discharge, right. So, disruptive critical voltage is reduced due to dust and dirt, hence coronal loss is more, right. So, if effect of dust and dirt, actually it increases the coronal loss. It makes your some percentage of the total power loss of the transmission line. When you are calculating transmission line power loss, those things are not considered, right. We consider for load flow studies, while doing it, you are making only I square R loss, but we are not considering coronal loss. But when they design the transmission line, they consider all these factors, right. Then effect of conductor configuration. Generally, conductors have two types of configuration, one is horizontal, another may be triangular, right, or another may be vertical also. 3 conductors may be horizontal plane, right, distance between AB, BC, AB is D, BC is D, then AC will be 2D. So, horizontal planes, symmetrical. Similarly, vertical also you can make it, similarly vertical way also you can make it. Another thing is that triangular, either equilateral or may not be, right. So, in that case what will happen, the conductors of 3-phase overhead transmission line, it can either horizontal or vertical configuration, right. First come to horizontal or vertical configuration. The electric field intensity at the surface of middle conductor is higher than the outer conductors, right. Whether it is a vertical or horizontal, one conductor will be there at the middle, A, B, C phase, say B is in the middle and A and B is in between A and C, right. Therefore, the disruptive critical voltage for middle conductor, your what you call disturb for middle conductor will be less than the 2 other outer conductor, hence there will be more coronal loss in middle conductor, because the difference is Vn minus V0. So, Vn is actually line to neutral voltage and V0 is disruptive critical voltage. So, for the middle conductor, if V0 is less, then Vn minus V0 will be higher. So, naturally your what you call that middle conductor, your what you call, hence there will be more coronal loss in the middle conductor, because your Vn minus V0 will be your what you call high, because V0 will be less. That is why that the middle conductor is higher than your what you call the electric field intensity at the surface of middle conductor is higher than the outer conductors. Therefore, the disruptive critical voltage for middle conductor will be less, that is V0 will be less, right. That means Vn minus V0 square will be higher. Therefore, the middle conductors your coronal loss will be higher than the your what you call hence there will be more coronal loss in middle conductor than the outer 2 conductor. This is the reason. Now, if conductors are placed equilaterally, say equilateral triangle, the average electric field intensity at each conductor will be the same, right, because it is equilateral triangle. See, the ground actually is at always equipotential surface, while computing your what you call capacitor thing, considering the effect of ground in the capacitance chapter in power system analysis course. At that time we have discussed this, right. If you want to brush up your memories, just I request please go through that your what you call that chapter, that capacitance chapter. Therefore, the electric field distribution is affected by the presence of the earth, right. Coronal loss will be less if conductors are placed your what you call at more height, but if you, that means the tower height will be more, but if you increase the tower height, then your what you call the cost will be more, because construction of the your tower of the cost will be higher. So, some optimum design is required, right. So, these are general phenomena. Next is the effect of corona on line design. Now, transmission line are designed in such a fashion that the corona loss is small enough in fair weather condition. That is true. If you design a transmission line, if corona loss is higher in fair weather condition, that is not acceptable, right. But because corona loss reduces the efficiency of the line, because when you are considering for computing the efficiency of the line, at that time we consider the losses. So, during fair weather condition, that corona loss should be low, right. If the disruptive critical voltage of about 10% more than the your operating voltage, then it is acceptable, even though some corona loss will take place when foul weather condition. I mean, if your disruptive critical voltage 10% more than the operating voltage, then still it is acceptable, right, even though some corona loss will take place under foul weather condition. Generally, corona loss under foul weather condition will be as many as 10 times higher than the fair weather condition, right. So, when normal temperature or your normal weather, right, there will be no rain, no snowfall, nothing is there, right, at the fair weather condition, right, in that case corona loss will be low, but foul weather condition it increases actually. That is why I am telling you, during rainy season another thing you will see corona loss increases, right. And another thing is an increase in DEQ and R increase the disruptive critical voltage, because it depends on the natural log or log base 10, that is ratio DEQ upon R, right. Thus, reduces the corona loss, but increases the cost, right. So, because if you try to increase the radius, naturally the conductor diameter will be more, then the volume will be more, and at the same time your cost will increase, but there are many other issues with the increase of diameter, this thing radius of the conductor or diameter of the conductor, because when you will go for sag and tension and analysis, at that time we will see that, right. So, these are the some of the your what you call that effect, different type of parameters affect the corona we just discussed, right. So, this chapter is very interesting and easy. Next, we will take your example, say this is example 1, right. So, here the look, conductors of a 3-phase transmission line are equilaterally spaced, say 6 meter apart, right. The radius of each conductor is given 1 centimeter, the air temperature is 30 degrees Celsius and pressure is 740 millimeter of mercury, right. So, if surface factor is 0.83 and irregularity factor is 0.92, you have to calculate the disruptive critical voltage and visual critical voltage, right. This is the thing. So, all parameters from equation 43, air density factor delta is 0.392 P divided by 273 plus T. So, P is given 740 millimeter and T is equal to 30 degrees Celsius. Substitute, you will get delta is equal to 0.957, right, that is the air density factor. Next is, now another thing is that next from equation 40, disruptive critical voltage, that is V 0 is equal to 3 into 10 to the power 6 upon root T root 2 R delta m 0 ln dq upon R volts, right. Now, data given m 0 is given 0.92, delta just we have computed 0.957, R is equal to 1 centimeter is equal to 0.01 meter, and as equilateral spacing 6 meter each sorry. So, DEQ actually 6 meter. So, V 0 is equal to 3 into 10 to the power 6 by root 2 into R 0.01 into delta 0.957 into your m 0 0.92 ln 6 upon 0.01 volts. If you compute this, V 0 will be 119.475 kV, it is RMS value, because we have taken this RMS value divided by root 2, right. Now, from equation 42, visual critical voltage, this is the formula for visual critical voltage, V suffix V is equal to 3 into 10 to the power 6 upon root 2, that we have seen earlier, it is mV into R into delta in bracket 1 plus 0.0301 upon root over r delta ln dq upon r volts, right. So, this is your visual. Now, we have to substitute all the data mv, r, delta, everything is given, dq, r, everything is known. So, if you put that that V v is equal to 3 into 10 to the power 6 upon root 2 into 0.83 into 0.01 into 0.957 in bracket 1 plus 0.0301 root over your r delta, r is 0.01 and delta is 0.957 ln 6 upon 0.0, and if you compute this one, then V b will be 140.95 kV. This is the RMS value, right. So, visual critical voltage and disruptive critical voltage, we got it. Next one is a example 2, this is example 2. A 3 phase 220 kV 50 hertz 200 kilometer long transmission line, right, consists of 3 stranded aluminum conductors spaced triangularly at 4.8 meter. Radius of each conductor is 1.5 centimeter. The air temperature is 27 degrees Celsius and pressure is 740 millimeter of mercury, right. If the breakdown strength of air is your 21.1 kV RMS, this RMS value is given per centimeter and the surface factor is given 0.85, compute disruptive critical voltage. Also determine the visual critical voltages for local and general corona. If the irregularity factors are 0.72 and 0.8 for visual corona local and visual corona general respectively. So, these are the things given that you have to find out, right. So, okay, we will be back soon. Thank you.